Okay, good evening, everyone. There is a question: is there going to be more added to the notes for the Unit 9? Yes, it will be added, but whatever is there for quiz purpose, you don't need to include the whatever I'm going to add, because for the tomorrow's lecture, I will be adding this deep reinforcement learning topic. There will be more content. Yeah, but you should read no matter whether it's for quiz or not. Okay, guys, let's get back to the point where we stopped. If you're in the last lecture, you know that we can define the model, the Markov decision process, as a phi tuple, where you have a state space S, then you have a action space. T is a transition of the state. Uh, the probability, conditional probabilities, which T is the conditional probability which defines how transitions are happening in the states based on the action taken and the current state. And you have rewards, these are random. And finally, we have a discount factor. This is the model given to you. Agent has no control over, apart from except one thing, where agent can decide what actions to take and when to take. That's in agent's hand. That's called policy. Let's look at what are the policies we have. So from now onwards, we denote all possible set of policies with capital pi, and small pi is a particular policy in that, obviously. Um, in the student engagement example we saw, there are two actions, 0 or 1, and S is 1 to L levels. So uh, pi can actually give us, for each state, it can actually give an action, or it can actually a probability distribution. Okay. How do we define that? First case is called deterministic, which is for every state, it maps to one particular action. Think about this. You have 1, these are 2 up to L, and pi maps pi of 1, either it's 0 or 1. Let's say we are taking 1, and pi of 2 also 1, action 1. That means when engagement level is low, we will like stimulate the student so that they will improve performance. And finally, there is no need to engage here because you are already in the state. No need, but this is a policy one can follow. Like you can withdraw your stimulation. You do nothing when you are in the highest, when the student is in the highest level. So you can think, okay, up to 8, I will engage. From after that, I will make it 0. Okay, that can be one policy. Take L is equal to some 12 or something. That is a policy. Such policies are called deterministic, and there can be stochastic also. Here, instead of having a one unique action for each state, you can very well say that, okay, 1, and pi actually is a vector, probability vector, so that say for we have two states, for this is yes, right, this is state. For this I have two actions. One is a half probability for 0, half probability for 0. Or more meaningful, let's say this is 1 by 5 and 4 by 5. I will engage with the student with probability 4 by 5, and do not with do nothing with 1/5 time. And for second also, maybe you can have same thing, 1 by 5, 4 by 5, 0 and 1, like that. And the final state 12, we can say that okay, I do nothing in this. Yeah, that can be policy. So here pi is actually mapped to a probability vector rather than a particular state. So when you're in state 1, what you do, you draw sample action from pi. That is what stochastic. So obviously all the probabilities actions, so this is integral is wrong. You can take a is equal to a, because we are talking about discrete spaces. S a is equal to 1. Okay, this is the condition needed for stochastic policies. All right. So just to illustrate this point, what is happening here, you start in a state, say S naught, and you or think of it as a robot in an environment, new environment. It system is in state S naught. It observes around and it sees the state S naught, and it selects a policy. It follows a policy, and in S naught, it takes an action. Let's denote with A naught. That action and the current state combined gives a reward. Okay, average reward or not. That also triggers a transition to new state S1, and this process keeps happening as the robot moving, learning. It changes. It's changes its action according to that. And all right, this is the illustration of what is happening in Markov decision process, where you have complete fully you can fully observe the system state. What is the goal of the agent? Would this be represented in a matrix? Okay, let me. Yes, of course you can, because I'm guessing you're asking about pi s comma a. You can write a matrix for all s in s and a in. Yeah, definitely you can write whole policy as this direction. You can take s and yeah here. Yeah, good. What is the goal of the agent? You have seen already what is the goal of the agent. It's maximizing the discounted, total discounted reward expected, maximizing the expected total discounted reward. How it is defined? For a given policy. Huh. Did I mention that we are looking at stationary policies? I don't know whether I covered yesterday or not. Yeah, what is a stationary policy? Stationary policy and non-stationary. Um, we say it's a stationary policy if it doesn't depend on time. It makes sense to pick stationary policies because your action should correlate with what is the state of the system rather than uh, time. Okay, if system is in the same state today or after 10 days, you would like to take same action irrespective of this year or next year. So we focus on stationary policies here, which doesn't depend on time. So the pi is stationary here. Each time step you're following the same pi, and that is conditioning on pi means. And you started in state S, and you're moving from one state to another, S naught to S1, and again you take action and you move to S1, the S1 to S2, and you take action according to pi, and you get rewards in each time you make a step. And then for that policy, the value function is defined as follows, and it's just a discounted reward. And your goal is to maximize expected value of this. Because of stationarity assumption, we can say that no matter what happened so far, if I'm doing the same thing and I'm at time t rather than at time zero, I'm at time t and in the same state, I'm following the same policy from there. From there, I'm applying discount, okay? Not from time zero, but rather I'm applying from t onwards. Then the value, expected value should be the same. That is intuitively correct, and you can easily show it using um, Markov property and stationarity. Okay, finally, what is the mathematical representation of the agent's goal is essentially this, solving this problem. You have several different policies, pi, and you want to find uh, the pi which maximizes. So let's represent that with stars, and this is essentially v star is essentially v pi star. If pi star is the optimal policy, to simplify the notation, we remove this and just use pi star. So what we are asking, we are seeking arg max. Yeah, that's what we are asking. Like for all s, we compute that, and then you have policy, the optimal policy. There is a good news. That is, we have deterministic policies as well as stochastic policies. There is a good news, that is this theorem, which states that there exists one optimal policy, that is deterministic. So you no need to map into a probability vector. You can very well say that, okay, I just have phi of s, just a vector consists of this. It tells me what action to take for each s, and that is deterministic. And surprisingly, if you look at the math, it's not surprising, but uh, if you look at this, it says that you don't need to go through all the probability distribution. That's more complicated. Then just look at the deterministic stationary policies, and you find an optimal one in that set itself. Okay, stop me if you have any questions. You can unmute yourself and we can have a discussion. Okay, that's interesting. So that's what I'm explaining here, that one can actually say that the set of all this set, all the policies, you can very well restrict to deterministic policies. Okay, when you're looking for, so you don't need to look at stochastic. Okay, and the next interesting thing is writing Bellman equations. That's actually shows us how to solve these problems, and let's look at it. Okay, for any policy, take any policy, stationary, stick to stationary for now. For any policy, what Bellman equation says that, so far we have, okay, what is it? V pi of S definition? It's expected value R is A, we have S prime. These are picked according to pi. This is pi of S, and this is transition probability S prime. Okay, that transition probability plus gamma, and terms will continue to happen in the summation. Then S prime in S, then transition probability, again the reward corresponding to this, and you have infinite summation. So you, from the stationarity, we have observed that, okay, once you are in this, maybe it's the same value we can expect, gamma multiplied. Okay, if you take out first reward and take out gamma, and the remaining summation should look like a value function again. That's what exactly this theorem says. Okay, take off take out the reward you get at the first step, and the remaining terms actually can be represented as value function itself, starting from there in the state which is next state s prime. Okay, and that transition happen with this probability. So this is easy to understand, it's intuitive, and that's what we are proving here, and it's easy to look at it. So what I just said, if you take the value function, you take out the first reward you get time 0, and it transits to s1, and after that these are the remaining discounted rewards. Okay, and if you split the expectation on these terms, this is easy to write based on what is the expectation we're looking at, and after that we have the all the future rewards, the discounted future rewards, that can be easily replaced with a value function starting from that state, and that gives the required expression. What is the good thing about this expression? You see value function appearing both sides, left side and the right side of this equation. So if you remember the contraction mapping we have seen, we have observed such situation, and we slowly coming to that point. Okay, next interesting result is a Bellman equation. This is exactly called equation for value functions. All right. When it is optimal policy, that is pi star, we take, if you are actually you started at state S, and from there you are applying optimal policy for which you get maximum value, you have this recurrence. This is slightly different from this expression if you observe. Here we have this transition probabilities. What we are saying is that we can very well actually compute, find the maximum action that maximizes this quantity. We are not looking at when you are applying maximum, we are not looking at policy as such. What is this RSA here? This is expected reward when you are in state S and take action A. What is the expected reward? That depends only on transition probabilities T. It doesn't really depend on the policy because you are already taken. It says that instead of following a policy, just maximize this, and when your policy is like that, from if it is an optimal policy, that's what you're playing from step one, time one. Okay, at time 0, you just need to maximize this quantity. That's same as from time 0, you playing according to that policy. That's intuitively correct, because if you don't do it, you actually can show that V star is not really optimal. This is not the maximum value you can get. Is this clear? If there is any question, please let me know. Okay, it's easy to look at the proof. V star is, of course, this is the definition of V star, the optimal value. And if you actually expand it, we have seen in this first theorem. Okay, from this we can write that this is this V star V pi can be written as follows. That's the same recursion. So instead of following pi, if I take a, here A is coming, here A is following pi of s. Instead of that, if I take A, that maximizes this quantity completely. Obviously, this has to be upper bounded. That's the definition of maximum. So you can actually upper bound it by this maximum. And after that, it's about just taking considering the definition. We have this definition. Same definition will give us V star of S. So what we got instead of this Bellman equation, which holds with equality, we got an inequality. Okay. And we need to justify why this equality. If this is not equal, then you can show that maybe using non-stationary uh, policy, you can improve the value function. That's contradicting fact that V star in fact the best you can get. So it has to hold with equality, and that's how we prove it. In fact, if you look at this paper, this one, it shows that there in fact the V star in fact a unique fixed point. Just the contraction mapping theorem we have stated earlier in the yesterday's lecture. This paper uses same contraction mapping theorem or fixed point theorem, shows that the V star in fact a unique function. So what is the dimension of V star? V star is defined for each S. So for the student engagement problem, V star, you can see it as a vector because I is equal to 1 to L. For each each engagement level, we have a one V star. So value function is a vector. Okay. And you can show that if you define a function to be in the contraction mapping theorem, if we show that f is f of s, if you define, sorry, f of x, let's say f of x is max so f has to take a vector from RL to RL. If you remember, it takes M to M. So here is L dimensional vector. So f is a function from RL to RL. So you have a, I think I'm messing up a little bit here. Let me write here for clarity. F is a function from RL to RL, L dimensional thing for student engagement problem. And let's define f of x. X is a vector, and for each term, what we have is that so max or S is one for that A plus gamma, all these transitions T you have here, but this is x1 summation S prime x1, this one. Similarly, you have max A or L A plus gamma, all this summation S prime T XL. Okay, I hope it's clear. It's a vector. So you can feed V of V vector. Okay, to this. Let's V star is equal to f of V star. This is what a fixed point, and it's unique. That's what we are saying. Okay. And using this say contraction mapping theorem, we can actually show that the V star is unique. This makes our problem easy because we already seen how to actually construct a sequence. Say you started with arbitrary V naught, and then you get f of V naught, then you get f2, f of v1, so on. And you know that it will converge to the fixed point V star. That's a hope. And yeah, I hope this is clear how it is connected with contraction mapping, which we had yesterday's lecture. Are there any questions now? Is everything clear? Okay, that is value function. Why we are looking at it? Because we are trying to uh, maximize that quantity. What we have in our hand, the policy, how we select actions. So we will see that sometimes it's like instead of looking at policy, you can always look at value function. And if you try to improve the way we did here, we can actually come to uh, the optimal value. Or you can also find optimal uh, policy itself. That also gives you optimal value. So there are the different kind of approaches to reach that final optimal point. In that process, one of the most useful function is called Q value function. Yeah, so far we have V is V pi 1 for a student engagement problem L. This is a vector, okay, L dimensional vector. These are the values, but here we define something called Q value function. That is more of a matrix, a two-dimensional matrix. It actually defined for both state and action. And how it is defined is exactly what is it says. Uh, you are in state S initially, and you are taken action A. That is what it says. Condition that you are in state S and you have taken action A, and you move to a different state. From there, you apply policy pi. Okay. In value function, you're applying policy from the beginning. Even in state S0, you follow the policy pi. Whereas in Q, for Q function, it says that, okay, I'm fixing both S and A, the initial state, and I'm following pi only from this time one. And what is the expected discounted reward I get? That's what is defined as Q value function. And it is so just like a stochastic policy, we get a matrix Q value function. Q pi is defined for both state and action, and we have two-dimensional matrix filled with values. And again, we can define what is the optimal Q value, just the way we defined the optimal value function. And that is uh, taking what is a policy, which actually maximizes reward, uh, okay, of this reward, expected discounted reward. So this is how you define Q star. The main advantage of Q star or the optimal Q value function is that once you know what is that function, you can actually compute what is the optimal policy pi star. You just go through all the actions, see which action maximizes the q value, and that's a 5-star we have. Only thing is that both uh, v star and pi star are depends on all future values, so we can't really look at few steps and say that, oh, this is a q star. Okay, we now look at algorithms that can actually tell us that can actually make us take decisions in a converging way, converging to optimal policy or q value or value function itself. Okay, these are called iterative algorithms. First one is value iteration. Before starting this, are there any questions? Seems like if so far, if it is not clear, let me know. Just drop a message. Is it clear so far? At least answer that. Is it clear? Someone respond. Yeah, that's good. Good to hear. Cheers. That's awesome. So yeah, people are following. Okay, first is value iteration. What we do here, again, recall that RSA denotes expected reward when you're in state S and take an action A, and the reward you get, what is the expected value. Can we compute it? If I give you, what are the transition probabilities? If I give you this S, A, S prime, this is a tensor, three-dimensional tensor. Okay, if I give you these values for S, S prime in S and in A, and also I give you what is the R, S, A, S prime. Okay, this is also a tensor is of same dimension. Can you compute them? You assume that these dimensions are small. Can someone say whether you can compute this value or not? Yes. So for each action, now think about the uh, uh, student engagement problem. There we have P0 and P1. They essentially gives you tensor this one. Okay. Compute taking the product of the reward and the transition forward and sum over it. Yes, that's correct. You just how do you write this? Go to S prime and take S prime and multiply this with R, right? Is this correct? No, correct? No, no. Am I wrong? I'm multiplying here. Len, Patrick? Yeah, that's correct. Yeah. So that is how you define expectation. So you have these transition probabilities and what reward you get. And this is exactly equal to RSA. Okay. So you have this reward and assume that in MDP, we have assume that we know these things. And when you, we also know what rewards to get as defined in the example. So we can compute this. So if you can compute that, then this algorithm can be implemented easily. What we do here, you start with some arbitrary initial values, and we are fixing small epsilon just to for convergence. When value is not changing too much, we'll stop it. Okay. There is a question, but we do that for all initial states and all actions. That's correct. We do it for all of them. So for all, you have now another matrix. that is S A, takes S and A here, and again you have values here. So you have another matrix that is okay, already one, you already computed those values and kept it in somewhere in the memory, and you can use them whenever you want. So think of a table. You need to pick the values from that table, and now started from V0, and you apply this recursion. Since you know these transitions, and you started from V0 and V1 you get in the first iteration, and you do it for every state. And you can also like update a policy. Yeah, that doesn't really play a bigger role here. It just to find out the policy. You can also do it at the end, and okay. But what you see is that the optimal value can be computed if you run it recursively and stop it when it is the change is not too much. Does anyone knows what is this metric? Can someone say what is it? Say I'm applying a vector y. The max norm. What is this? So you just take a max of y. Yeah, that's a norm, and you want this to be less than epsilon. If one element is this max is less than, then it shows that for all j it is smaller. So it's a good metric. It's yeah, and you stop when this happens. That gives a good convergence, and you can show that uh, because it's a unique value, this optimal value, you converge to that, and that's what is proven in this theorem. We are not proving this on class, but yeah, this is the result. It shows that in fact it converges linearly at this rate, and gamma is less than 1. Remember that. So as k increases, this is going to 0. This is a fixed value. Okay, it just depends on first iteration and the 0th iteration. This is optimal value, and it decreases at this rate, and eventually it goes to 0. So your algorithm will terminate eventually. All right, that is a value iteration. Now we have a q value iteration. This is an important thing for the later algorithms to understand. So again, we know that once you know q star, it's easy to compute not only uh, pi star, but you can compute optimal value itself, and so, that's why we got this pi of s is equal to, we know that this is max a, sorry, v star of s. This is arg max. So that's why we wrote arg max a. Yeah, q star of s comma a. Oh, I'm sorry, I'm confusing here. Ignore this statement. There is no a. Yeah, we know that this is pi star. Yes. Similarly, we have this this optimal value. If you look at how value function is defined, this is how you just look at the Bellman equation, and you can conclude this. And also we can show that Q value function also satisfies a Bellman equation. Earlier, we have shown for Bellman equation for V star of S for each S. Here we have not just S, but a pair, S and A. Okay. You take each term in the Q star, and we have a Bellman equation, right? Again, we don't know what is this Q star. So we can build, construct this similar iterative procedure. You start with Q star, unlike Q0, unlike V0, which is a vector. Here you have a matrix. So start with a matrix, and again you stop, terminate when the error is small. Just like a value iteration, Q value iteration also takes the previous values and substitutes. We have this result. Yeah, what is this star? This can be, again, in the value iteration, we have this summation. This is exactly what we have here also. This is can be written, sorry, this term, second term can be written again, S prime, S, T, S, A, and max UK minus 1. Yeah, that is what we have. So we use this iterative procedure and compute. This is clear, right? Both value iterations. Okay, then we have a policy iteration. Here we actually trying to directly find what is the optimal policy, unlike earlier where we actually found policy itself. We want to find, we found value functions, V star or Q star. Here we are looking at policies, optimal policy we are trying to, and I don't go into much details. There is this step. Maybe I will update it tomorrow. There is one step we need to look at. This is not clear in this notes. I will write it down. But again, this is procedure is very similar. Instead of max only, we have our max. We again start in some policy, and we assume that the value corresponding to that policy is V0, and we use both policy and values, and we recursively update these values, and that's what we just you find max, and you can show that this one also converges. Yeah, for now I'll not get into that because we are mainly focusing on Q learning. Okay, what are the issues with these three iteration problems? Can someone say, just based on what we have seen so far, just small hint, what could be an issue? Why you can't implement? Suppose, assume that state space is higher, larger in dimension. What can be the problem? Anyone? No? Yeah, we need to compute this RS. Yeah, these are expected values, and that can be complex. Too expensive to check all sets, right? And too expensive to store also sometimes, and don't know all the transition property. Yes, so that is another thing. So far we are in MDP setup, so we assume that we know the transition probabilities, but in practicality we don't know these transition probabilities. That makes things more complicated, so we can't even compute this. Forget about the complexity on the, even if you have all the computational powers, we can't compute this. And yeah, all these issues are there. So first thing, now we will step into reinforcement learning setup, where we focus on one particular method. It's called Q learning. Here, exactly as someone mentioned, Alan mentioned that transition probabilities are unknown. That's what the setup for reinforcement learning. And if that is the situation, we try to actually, without knowing transition probabilities, we want to update the Q values. If you look at Bellman equation, or just look at the in this, yeah, this is what Q value iteration. We are using this particular transitions. At time t, you have Q values, and for each state, you update Q values as follows. This we don't know, and these are unknown to us. But suppose whenever you ask a sample, so whenever you take action, you know what state you will get. You can see the state. So state can be sampled by taking action. Okay. So even though we don't know this transition probability, this is expectation. This is essential expectation. Instead of expectation, we use random quantities directly. This is also expectation. So instead of expectations, we try to use a random quantity, whatever reward you get and whatever state you see, that random state, you will try to use them. And you essentially, this can be altered, and just like a stochastic gradient, you give weight to existing Q value, 1 minus alpha t. Initially, you want to take alpha t large enough so that you don't really get influenced too much with initial values of Q values, and slowly you can decrease alpha t. We will see what rate one has to decrease. And what it says that, okay, this is a expected value. I'll replace with whatever reward I get. And this is expected value. I'm just replacing with whatever Q value I see at the time t, and compute max. And gamma is, of course, it has to be there. And yeah, this is update for Q learning. The this update rule is easy. The difficult part is whether it will converge or not. We see that it indeed converges. What we do in this algorithm, you start with a state distribution. Okay, state distribution. You sample state, initial state from there, and you assume that that is the state you are in. This helps in exploring. Okay, even if some states are not seen in the second loop, if there are two loops, one is this and one is this. So in the first loop, you always start from a state which is sampled from distribution D naught, and that is what we are doing here. That is S naught. You start from time 0 again each iteration here, and in this second loop, inner loop, you essentially apply this update. All right. This, if you have confusion with this update, you can notice that this also can be written as qt s tat plus alpha t into delta t. I'm just writing this where delta is the second term minus q itself. Okay. So there are two parts. One is exploiting, that happens in this inner loop, and whenever you again start from some random distribution you have taken, okay, arbitrary distribution, that will make us explore. So think of D naught being uniform distribution on all the states, then it will give opportunity, that is exploring. And so that let us learn a little bit about each state. So the key result here you need to note is that if you, so like in the whole algorithm, you will visit different states, and whatever state and action pair you are saying, only those values you update. Okay. Other values you can't, if you haven't visited a state and action combination, the Q value corresponding to the state action pair is 0. So what it says that if weights are such that each state is explored enough but not explored too much, okay, then you have a convergence, and that convergence can be optimal. Okay, it can be converging to optimal. That's a result we have. This is an interesting results, and under certain conditions even Q can be Q star. Not only convergence, it also converges to Q star, and that's a take home point at this stage. And I just want to conclude this lecture by highlighting some issues here. Okay, even now, even though this algorithm is easy to implement and doesn't and like can require knowing transition probabilities. Okay, still there is a problem with high dimensional thing, like if S and A is large state, that is the dimension of Q matrix, then you need to actually do a lot of iterations. You need to run this algorithm really longer to explore and exploit all the elements in this S times ES set. Okay, that's not possible if you have budget issues like complexity, limited computational power, and but you have a high dimension. So think about this. Okay, you have states and actions, and this is a nice q value function. This each height of this each bar actually represents a q value. It's a nice function, but you might actually end up having a very sparse like this. It doesn't resemble anywhere close to actual q function, and so all these zero value things are not explored. So that's a drawback. And if you look at this thing, there is a smooth kind of a curve going on through it, and that is happens in many real-time application. Think about robot. Okay, uh, an action, a little bit deviation from the optimal action should not cost you too much. Okay, you might lose little bit reward. It path might deviate a little bit, but there is some sort of continuity and smoothness that is not captured in this algorithm. So if you know this point, okay, this you should be able to say that the next point also very similar to this. That's not captured in this particular algorithm, and that's what we see in deep reinforcement learning, that is deep Q learning, how we actually use function approximation such as deep neural network to overcome this issue. We'll see that in tomorrow's lecture. Any questions? I hope this is clear. Any feedback? Are you guys awake? Thank you, Rohan. Thank you, John. Yeah, hopefully you guys got something, learned something. Let's see, tomorrow exciting. Yeah, see you guys. If there are no questions, have a good evening. Thank you, everyone. Yeah, see you tomorrow.